Welcome to Ask and Learn.
We are given a differential equation, and the graph is a function involved in this differential equation, and we are asked to draw the slope field of this equation and to determine the limiting behavior of solutions based on a value of one of the variables. So the equation we're given is y prime equals f of y, and we're given the graph of f in red as a function of y. This is an autonomous differential equation because it's only in one variable, y. We know that y is some function of x. Draw the slope field. Suppose that c is some real number which is equal to y prime, and this is equal to f of y. So we get that c is equal to f of y for all x in the real numbers. So we can look at horizontal lines. Now, draw this on the x and y axes. Now we see that if c is, say, 0, we have that f of y is 0 at points -2, 0, -1, 0, at x equals 1 and x equals 2. So to summarize this, c equals 0, and it follows that y is equal to plus or minus 1 or plus or minus 2. And this is for all x. So we see that along the lines y equals 1, minus 1, 2, and minus 2, we have a slope of 0. Determining what some other slopes are going to be is going to be a little more difficult. We don't know for sure what the value of these troughs are. However, we do know there's a point at which function f crosses the fy axis. So we have the y-intercept. And so if c is equal to f of 0, well, we have that c is equal to f of y, so it follows that f of 0 is equal to f of y. And there are a few different points which have the same value as f of 0, one of which is greater than 2, and one of which is less than -2. So then we have that, well, y is going to be equal to 0, something that we'll call 2 plus epsilon, where epsilon is some small real number, and assuming this is a symmetric graph, -2 minus epsilon, really could have written this plus or minus 2 plus epsilon. And we see that f of 0 is certainly a positive number, so we will have a positive slope along these horizontal lines. For the sake of convenience, I'm just going to represent it as a slope of 1, but clearly it could be steeper or shallower, depending on the value of f of 0. And then for 2 plus or minus 2 plus epsilon, again, slopes of 1. And we see that as y gets closer and closer to positive infinity, f of y increases, and so the slope is going to increase. So we see that these horizontal lines, the slope is going to get larger and larger until these slope lines are almost vertical. To find the slope lines that are in between 1 and 2, we see that in between y equals 1 and 2, we have that f of y is negative, and it seems to reach a trough halfway between 1 and 2. So we have its most steep in the negative direction halfway between the two of them. And I'll represent this, again, for simplicity, simply as a slope of -1. And it's going to be hard to see in this graph, but the idea is that the slope evens out between these two extremes of slope of 0 and slope of -1. So I'll draw two examples, but it's going to be pretty hard to see. Just going to have to imagine sort of like that. And this is also true for y in between -2 and -1. Same idea. Find the slopes between 0, 1, and 0, -1. Again, we'll look at a graph. You see that between -1 and 1, f of y increases from 0 up to a point is f of 0, which we said was arbitrarily took to be slope of 1, and that's the peak. So we're going to have y equals -1, a gradual increase in slopes until we reach y equals 0, and then a decrease in slopes again. So this is an approximation of our slope field. And we are asked how the limiting behavior of the solutions of this equation depend on what value we picked for y of 0. So this is essentially asking if we choose our initial condition to be somewhere on the y-axis, what is the solution going to look like? Will it have a limit? If so, what is that limit? So I'm going to take a few examples. In black first, let's suppose that we take our initial value to be y of 0 equals to 0. And we see we point at 0, 0, and if we approach positive infinity, we start to grow until we reach about y equals 1, where we level off. So we reach an asymptote of y equals 1. In the negative direction, we decrease until we reach an asymptote of -1. So it's pretty clear that if -1 is strictly less than y of 0 is less than 1, then we see from this graph that the limit as x approaches positive infinity of y of x is going to be equal to 1, and the limit as x approaches negative infinity on y of x is going to be equal to -1. As another test, let's try the initial condition y of 0 is equal to, well, we can see clearly if we pick y of 0 equals 1 or -1, we'll simply have two horizontal lines, one at y equals 1 and one at y equals -1, and so we will have limits for those, but trivially, more interesting case, let's take y of 0 to be 1.5. Now represent this graph in red, and I'll have a twin graph for this. Call it y of 0 equals -1.5, which I will also represent in red. So we'll see that for the first graph, we have a point at 0, 1.5, and as we approach positive infinity, the graph levels off at y equals 1. As we approach negative infinity, increases until it levels off at y equals 2. Likewise, for a second graph, give the point 0, -1.5, and our graph, as we approach positive infinity, decreases until it levels off y equals -2, and as we approach negative infinity, increases until it levels off y equals -1. So we see that if -2 is less than y0 is less than -1, or 1 is less than y0 is less than 2, then we have that limit as x approaches positive infinity on y of x is equal to for our second case, y equals -2. So I'll actually separate these some more. And the limit as x approaches negative infinity, if y not satisfies this condition, on y of x is going to be equal to -1. And we see that if, like in our first graph, 1 is strictly less than y0, strictly less than 2, the limit as x approaches positive infinity on y of x is equal to 1, and the limit as x approaches negative infinity on y of x is equal to 2. And again, if we take y to be 2, or y0 to be 2, or y0 to be -2, we end up having two more horizontal lines which both have limits trivially. One has limit in positive and negative directions of 2, and the other one has a limit in the positive and negative directions of x of -2. So the last interesting case that we'll see is if we choose y0 to be greater than 2 or y0 to be less than -2. So let's suppose that the absolute value of y0 is greater than 2. So this means that we could have, in one case, y0 strictly greater than 2. Well, if I graph this in green, you can see from our slope field, we have the point. Let's pick some point, as an example, take y0 equal to 2.5. And we see that as we approach positive infinity, we quickly increase towards positive infinity, and as x approaches negative infinity, we decrease until we run parallel to y equals 2, sort of an exponential-like function. And so we see that the limit as x approaches infinity is equal to, as y of x approaches positive infinity, then we have that the limit as x approaches negative infinity of y of x is equal to 2. Now likewise, if we have y of 0 is less than -2, so take for example y of 0 equals -2.5, which again I'll graph in green. And we have a point at 0, -2.5, and we see that as x approaches positive infinity, the graph flattens out and runs parallel alongside y equals -2, and as x approaches negative infinity, increases quickly towards negative infinity. Again, like an exponential function that has been reflected across the x-axis and translated. So we see that the limit as x approaches positive infinity in this case going to be negative 2, and the limit as x approaches negative infinity on y of x is equal to negative infinity. To summarize, the limit as x approaches positive infinity on y of x is equal to negative 2 if we have that our initial condition y of 0 is less than negative 2. We also have that if y of 0 is equal to negative 2, this limit is still negative 2, so you can say less than or equal to negative 2. If y0 is between negative 2 and negative 1, then we saw that this limit is going to be negative 2 again. So you can actually extend this to be a set of all y naught less than or equal to less than negative 1. And we have that if y naught is equal to negative 1, that the function y of x has the limit negative 1 now, so this is different. So we have limit of negative 1, y of 0, 1 is equal to negative 1, and also, if it is, that is actually the only case in which it's going to have a limit of negative 1. So what if y of 0 is greater than negative 1? We see that if y of 0 is greater than negative 1, but is less than or equal to 1, the limit is going to be positive 1. Negative 1 is less than y0, less than or equal to 1. We have a limit of positive 1. And we see that if y0 is strictly greater than 1, but is less than 2, we still have a limit of 1. So again, we can revise this to get y0 strictly less than 2. We see that if y0 is equal to 2, then we have a new limit of 2. And if y0 is anything greater than 2, the limit is infinity. So we have a limit of 2, if y0 is equal to 2. And finally, we have a limit of infinity, positive infinity, if y0 is greater than 2. Likewise, the limit as x approaches negative infinity, y of x is equal to, the cases may not be exactly the same. So let's check a graph again. We have that if y of 0 is going to be less than negative 2, the limit's going to be negative infinity. If y of 0 is equal to negative 2, the limit's going to be negative 2. If y of 0 is greater than negative 2, and is less than 1, you see that the limit of x approaches negative infinity is -1. So from -2 less than y of 0, 50 less than 1, this is -1. If y of 0 is equal to 1, then we have the limit of y equals 1. If we have that y of 0 is greater than 1, then we see that the limit as x approaches negative infinity is going to be 2. So these aren't exactly the same cases, but it should be clear that we can use both of these to figure out, given a certain initial value, exactly what the limiting value will be. So this is our answer.